Okay, so I'm going to be explaining 10A through E. So essentially, we're starting with a massless spring of a spring constant of this value is connected to a mass of this value at rest on a horizontal frictionless surface. So there's no friction present. We don't have to worry about that. The mass is displaced from equilibrium by this distance along the spring's axis. How much potential energy in joules is stored as a result? So we start with this value in meters, 0.51 meters, and we're using this equation, P equals 1/2 kx squared, and then we have P equals 1/2 times this value times 0.51 squared. So we have x equals 0.51, and then we have k equals 7,098. So then we get this as our potential energy value, which is just P equals 923.095 joules. So the next question is how much time is required for the max KE as a result? So what we do is we have this equation, T equals 2 pi times m divided by k, and then we have 2 pi times the mass, which is 419 over k, which is 7,098. And so then we have the change in T equals 1.52398 equals T divided by Y, and then we have the change in T equals 1.52398 divided by Y. And so then Y is just essentially what we're given, which is just 0.51. And then we do divided by 4. Now, this is important. So because it has maximum kinetic energy at its equilibrium position, and the period is the time it takes for it to go back to the original point, you divide by 4. So the period covers 4 times the surface. And so in order to find the actual value, you have to divide it by 4 because there's 4 instances in which the spring oscillates. So then we have that's why you divide by 4, and I'll explain that more in part C. So the potential energy is stored in springs, is fully converted to kinetic energy. So we have this given value, 6.11 e to the 7, and then we divide it by the potential energy G that we found in A. And so then this is just what I was talking about, where there's 4 times the surface, so you just divide it by 1/4. Next, so spring is just different at time slots, like I said earlier. And so then to find the average power, you do work divided by time, and then the amount of energy divided by time energy released over time found. So we're using this formula, which is just P average equals starting time times potential energy divided by change in T. So we have 6628208 times 923.1. Sorry, I'm literally butchering that. Divided by 0.381, which is just our period time. And so then we have A times C divided by 0.31, which equals 1.0606 e to the 10 watts. So that's the average power. That's just a number, like the average power number given to us. So we just use this formula that I found. So then E is just the given value that we just found divided by e to the 5th. So e to the 5th was given to us, so like it could have been like e to the 6th or anything, but like you would still do the same method. You would just use what you found in D divided by the number. And e to the 5th was given to us, like it was like written in the formula, so it's not like I just made this up. And I get 160,600 buildings. And so just coming back to this point, it's still divided by 4 because there's 4 times that the spring oscillates, covering one period. So you just have to divide by 4 because in order to find the period for the whole thing, you have to divide it by 4, because if you didn't, then the period time would be wrong, because that would be like time for one of them, or like time for all of them. And then to find time for one, you have to divide it by 4.